So last time we started talking about rational equations. We spent a fair amount of time talking about finding common denominators for things. Again, you want to find the least common multiple. So if there are common factors, you take that into account. And then otherwise, basically, you look for sort of covering all of the individual pieces that are involved. So if you do this for numbers, this is like a prime factorization thing, basically, right? Like make sure all the factors are in there. For things involving a variable, the basic idea is that you have to treat things that aren't identical as though they're separate factors. You got to treat them like they're grouped. So the x plus 2, the x plus 7, that the individual pieces of that, right, the x and the 2, those are, super glued together. Like I can't separate those. I treat them like they're grouped. That means to figure out the least common denominator, I just need to include both of them. They don't have anything in common, so we just include them both, and that's our LCD. You've had some more time, right? It's been a couple days since we've seen each other, so I hope you've had some more time to sort of think about and work on and do some problems here. But is everybody feeling pretty comfortable with that idea, that part? Okay. We're holding our peace if not. So what's the least common denominator for these then? It's got to have a 2x because one of the denominators has a factor of 2x. What else does it need to have? An x plus 1, because one of the denominators has a factor that looks like x plus 1. What else? An x minus 5. There's nothing common to any of these, right? There's just these three distinct separate pieces. So the LCD is just their product, right? There's no way that I can, sort of like double count anything or get more mileage out of one of these pieces. They're just three separate things. The LCD is just their product. Everybody okay with that? Yeah? Okay. All right. So that's, one part of the conversation is identifying that least common denominator. Along with that, or, maybe at the same time as we're doing that, we can think about domain issues. Because after all, these are still rational functions. They still have all of the, sort of baggage that comes with the domain from, like the thing on the quiz we just talked through. Because they're rational expressions, the denominator cannot be 0. And if there's a variable in the denominator, that means that, well, there might be some times that it would want to be 0, right? What would make this 0? If 2x was 0, then x would have to be 0 as well. Right? Because it's 2 times x. So 0 would be a problem. What would make this one 0? -1. And this one? 5. So whatever else happens, x cannot be, right? These things will be undefined at -1 or 0 or 5. If we wrote out the domain, it would be like -infinity to -1, -1 to 0, 0 to 5, 5 to infinity, right? Something like that. But those three values are problematic. So if we work through this thing and we solve and I see any of those show up, I know I need to exclude that, right? Or toss that out. That's like an extraneous solution or like a false positive kind of. Okay. The way we actually use the LCD is to take our equation and multiply by it. Now, I'm not actually going to do that with this one. Like I wrote this down just kind of on the fly to get the LCD thing to like be able to talk about that. Actually multiplying this out is maybe going to get kind of messy and maybe lead to some like really weird solutions and stuff because I didn't, build it with that in mind. So I'm not actually going to do it for this one. We'll do a like real example in a second. But if you multiply by the LCD, well, the way that we built it up in the first place was to take all the denominators and all of the fractions in the whole problem, and make sure that like it sort of covers or includes all the individual pieces, right? That means that when we multiply, like for example, think about multiplying this by this. When we multiply those, we're going to get a bunch of stuff that cancels, right? Like that first part of the product, 2x would show up in the denominator because it's already there, and in the thing I'm multiplying by, so in the numerator, those reduce then, those cancel. So it would be like the first part of that product would be the LCD times 3 over 2x, that over 1 if you want, and then you're like multiplying straight across. So that part cancels, and you're left with all the rest of it. 3x plus 1, x minus 5. Okay? Okay. And then the same similar kind of thing happens everywhere else, right? This part of the product, the fraction that's already there has an x plus 1 in the bottom, so the x plus 1 is going to cancel, and we're left with whatever's left. This part, there's an x minus 5 already in the bottom. Those would cancel, and we're left with everything else, right? So basic, kind of want like a, I don't know, step-by-step kind of thing. We need to find the LCD. The point of finding it is so we can use it. So we use the LCD to clear out the fractions, right? Multiply the whole thing by the LCD, and then because of what it is, all the fractions go away, right? Because we get all this stuff sort of canceling and reducing out. And then that's going to leave us with some kind of thing that we're more comfortable solving, right? That's going to turn into a polynomial of some sort, so we solve it. That feels like it deserves an exclamation point, so we'll go with that. Solve whatever's left, right? It's going to end up like, I mean, in theory, it's just any kind of polynomial, but stuff that you'll actually see, like I went through the homework this morning and went through everything, my notes, test questions, whatever. It's going to end up being either a linear or a quadratic, because those are the things that like we know sort of everything we need to know about solving in general. So you just solve that. It's something you know how to solve. And the one sort of overhanging like catch thing is this part about when we solve, we might get extraneous solutions that show up, right? We might get like false positives. If I solve this thing and I got, I don't know, 2 and 5, well, 2 is fine, but 5 is a problem. So I would throw it out. Okay? Okay. That's the big picture idea. Let's actually work a problem. So let's take a few minutes and y'all give 3A a shot. That should be a not too out there version of all this. Okay, yep. So, well, so you're distributing. So think of like asking people to be accepted. So his name for this. For like different things. So I have this. So there you go. We also need its expiration. What's that? And then do the same as the other side. Yeah, I think it some. Wait. So. There's multiple. Right. I asked. Then since technically shows up on your factory. So what's that? So then sort of put it all together. On the left hand side, close. It's only can't do this thing, just like you can do so many parts. Right, like you did. Should be exposed to. Equals 5. Yeah. X plus M y. Okay, yeah. So at some point we switch. Right? So you got this equals 5. Equals 5. Remaining. 13. So stay in intellectual terms. So. Okay, and then once you get everything into terms of like you can basically just ignore that. X plus 11, 3, 6, 5, 1, 3. Yeah, it's linear.
Which that's only
you
one
can
more
use
step.
the Let's one have that first. So,
X plus 7.
right, so those parentheses are the
Right.
so it's that plus. What's 30 times x plus 2? Okay, so you got x plus 7 plus 3x equals 6. do that. Okay, what is the, oh wait, no, I didn't need to do that, sorry. What is the least common denominator here? Why? Yeah, because this factors as x plus 2 times x plus 7. You might be thinking, but Dr. Thomas, I don't want to have to factor stuff. Well, what might be really good guesses for where to start with factoring this thing, even if you don't really love factoring things? What do you get when you multiply these? Two x, 7x, 14, 9x plus 14. I know you can't always, trust the this problem seems really involved or not, or everything, and we might have different gauges for what is, straightforward or what is a lot of work. But if this is some other quadratic that doesn't have x plus 2 or x plus 7 as its factors, the LCD is going to be like a lot to take in, right? If it's the product of all those things. And that means when you multiply through and clear out the fractions, you're going to have some like, I don't know, degree 4 monster that like we're probably not going to be able to solve. So if you see a bunch of like linear factors and maybe a quadratic somewhere, even if it's not factored, the first thing I would check is, see what you get when you multiply those linear factors out, because it's probably the other thing that you're dealing with, right? Otherwise, it's just going to be computationally like kind of beyond the scope of what we need to be able to do. So that factors is x plus 2 times x plus 7. The flip side of that would be, if you see a quadratic, just start by factoring it. It's probably not a bad idea. So our LCD is that product then. And along with that, let's see, I'm going to write this in like, so like if this had been let's say the denominator here had been like x squared plus 6x plus 8 or something, right? Then the LCD is going to be that. And when I multiply through, yeah, I'm going to get to cancel a little bit of stuff, but that first term is going to give me a cubic. And the second term is going to give me a different cubic. And over here, I'm going to get it like that's going to be a lot. So I'm not saying that that can't happen. I'm saying it's not going to be something that you need to worry about in your immediate future, right? Like out in the world of like math things that can happen, yeah, it's a real thing, but it's not something that's going to come up. Okay. Uh, sorry, let's put things back where they went. Okay. Now, along with this, because again, I like to kind of front load this part. What are all the x values where things here are undefined? -2, -7, and then this one, either of -2 or -7, right? So whatever else happens, x can't be -2 and it can't be -7. Again, I know I'm being a little bit ridiculous about this, but like I'm writing it in gigantic, bright pink letters so that, once I work through stuff, like I can't help but kind of be thinking about that, right? Just so it's, front of mind. All right. Now let's take our equation, multiply by the LCD. One thing at a time, right? That's going to get distributed across that the two terms, on the left-hand side. But first things first, x plus 2 times x plus 7 divided by x plus 2 really is what's going on. What happens? X plus 2 cancels. What are we left with then? X plus 7, right? Whatever part of the LCD didn't cancel, didn't reduce out. So x plus 7 and 1, because that was the numerator of that term. So x plus 7 times 1. Okay. Now this part, x plus 7 cancels. So we're left with 3 times x plus 2. Or x plus, I guess, yeah, I did write the other one in the other order. It's multiplication, so it doesn't matter. But just so I'm, being consistent. This is the surviving part of the LCD. This is the numerator that was there, right? And then on the right-hand side, all of it, because x squared plus 9x plus 14 is x plus 2 times x plus 7, right? So it cancels the whole thing, and we're left with 5. Once we take care of it, it's like, like you can draw a dotted line here if you want to. Just ignore everything up there, just about, and just focus in on solving this, right? We get to, sort of take a whole new look at the thing. This lets me look at it from a different perspective that is hopefully more familiar and more comfortable, right? So we solved that. What's x plus 7 times 1? X plus 7. What's x plus 2 times 3? 3x plus 6 and 5. Okay, so to solve that, x plus 3x, so combine like terms, which is 4, 7 and 6. This is a linear equation, so solving is just going to be moving stuff around, right? I'm going to subtract 13. Divide by 4. And we get that x is -2. But according to the gigantic pink letters at the top of the page, right, it can't be. Or, go back and check or whatever, however you want to like frame that part of things. But at some point, and this will be true for like other stuff that we see down the road as well. If you start with an equation that involves things that have domain restrictions, right? That where the question, what's the domain of this, would be interesting, and I have to work something out, then I need to make sure that whatever I get as solution still work in the original problem. If I try to plug -2 in, for example, I get 1 divided by 0 right off the bat, and no, that doesn't work then, right? So this is no good, which means this has no solution. Which I know is a little anticlimactic because we just did all this work only to find out that there is no answer, right? But I mean, the fact that there is no answer is. So there's nowhere that these things meet because the only place that they maybe could occurs at a vertical asymptote, right? Okay. Questions about any of that? So again, just to kind of go through our workflow thing, we found the LCD. The LCD gives me a way to get rid of the fractions, and then we solve whatever's left after that with the, again, sort of, catch that we need to make sure our solution makes sense. Okay? All right. Y'all talk me through B then. Okay, let's see. You said like x times x squared? Okay, that would definitely be a common denominator, right? Because one way to get a common multiple is just multiply all the stuff together. Is it the smallest one though, right? That's the L part, the least part. So let's think about this in a like kind of numeric example. If I want to take 1/9 and 1/3 and combine them, what's the least common denominator for 9 and 3? 9, right? Because you have to go up. I can't reduce this any further. But I can, I don't know, unreduce, right? I can take this one up. Because what we're allowed to do is multiply by missing stuff, right? I can multiply this by 3/3. If you want to think about it in like, slices of pie terms, I don't know if that resonates with anybody else the way it does with me, but like, if I've already cut the pie into 9 pieces, I can't glue them back together, right? But I can take this other pie that's cut into 3 pieces and I can cut them smaller, right? Like that's what you're doing when you change denominators. So I can take them both up to the, larger of the two things, right? Well, 9 is 3 times 3, right? Okay, so if I've got one denominator that's x squared, which is just shorthand for x times x, and the other one is x, then what's the least common denominator for those two things? Just x squared, right? Because I could change this one to match this, but I can't go the other way, right? I can't take out stuff that's already there. All I can do is introduce more stuff. So I can take this up to x squared, but I can't take this down to just being one factor of x. So the least common denominator would be x squared then. Again, x cubed would be a common denominator. It's just that when I go to solving then, everything's going to be like one higher in degree, and that's maybe going to make my life harder, right? So it's a little less important with number stuff to actually get the lowest common denominator because you just reduce it out at the end anyway. And it's numbers, and we've done fractions forever, right? So like we're more comfortable with that. Here it's going to have implications for like what the equation looks like and how solving it goes and all that kind of stuff. So we kind of want to spend a little more time to make sure we get the smallest one. Okay, so is everybody okay with how we're getting that x squared is the least common denominator? If this had been that. If our denominators were x squared next to the fourth and x, what's the LCD then? X to the fourth. I have to go with the highest power because I have to like add more stuff in, right? I have to build up. I can't take away. So if this has 4 copies of x, I can put 2 more in here. I can put 3 more in here, but I can't take away from what's already there. Yeah. Like that? Like, okay, just like toss it. Then yeah, it would be x cubed. Yeah. Yeah. So if they're, just single terms like that, right? They're all the same kind of thing. Then we just need to build up to whatever it is. And the same thing would be true if it was like, I don't know if I'm going too far afield here, but something like that. The LCD would be, I definitely need an x plus 1, but how many copies of it? 2. And then also x minus 5. Right? Okay. Okay. Back to the matter at hand. The LCD is x squared, and no matter what else happens, x cannot be 0. X can't be 0 because if it was 0, we'd be dividing by we'd be dividing by 0, and dividing by 0 is right. Okay. You don't need to be embarrassed. It's fine. It's so I can make sure that my children aren't on the other side of the house trying to unalive each other, right? Okay. Okay. Now what? Multiply the whole thing by x squared. What's the left-hand side look like? 7 minus 8x. Here, x squared cancels entirely, right? And then here, we can reduce by 1, right? X squared divided by x reduces to just x. So I've got x times 8. Then what? We've gotten rid of all the fractions. So we're at, step 3 on our flow chart there. Now we should just be able to solve this thing. What kind of thing is it? Right. So how do we solve it? Yep, make it equal to 0. So get everything to one side. So I'm going to move this over by adding. I'm also going to rearrange. Just be careful when you do that. Make sure, keep in mind that the sign goes with the term, right? So negative 8x, 8x is negative, 7 is positive, so it's plus 7. To move it over, you add it. Right, you do the opposite. It was negative on the right-hand side, so when you move it to the left, it's positive. Yeah. Okay, then we need to solve this quadratic. How do you want to do it? Yeah, no factors. Factors how? 7 and 1. They would need to both be negative. factored so we can split them up. We get 7 and 1. Which are both not 0, right? 0 is the only place that we would have like a domain issue here, right? The only thing that would make anything defined or undefined. That means that either one of these is fine, right? They're both okay. They're both valid solutions. Those are our answers then. Again, however you want to go about that part, right? If you're more comfortable just saying, forget it, I'm just gonna, plug this into the original equation and see if it works. Like, by all means, do that, right? That's not wrong. I'm saying we don't have to go that far, because what we need to check is that these don't make anything undefined, right? 0 is the only thing that would, neither of these is 0, so we're good to go. Do something though. I mean, you need to be thinking about it all the time, right? Anytime you solve one of these, this, do those work in the original equation question needs to be part of the process. But even when, everything I get as a possible solution, even when they all work, like here, right? I got 2 things that could work, they both work, great, here are my 2 solutions. Even when they both work, make sure that you're doing, like that you're writing something down, looking ahead to like a test question. Make sure that you're writing something down so that I can tell that you've thought about it, right? So, okay, it's not done yet. I mean, you can come in if you want. Spoiler alerts for later. No, you're fine. If this is what you did on like a test question, right? Like everything here is correct. The work is perfect. There's nothing wrong with it. But nothing about what's written down tells me that you've thought about the fact that the thing you started with has domain restrictions and has the possibility of solutions that don't work, right? Everybody agree? Because I moved all that stuff away. This is going to cost you a couple of points because again, I can't tell that you've thought about the fact that there are places where this thing doesn't exist, right? Ways you can fix that. Well, you can do, something like what I've been doing and like start off by writing a note about, hey, here's what the domain looks like. I've thought about it. Or you could get to these and you could say, like, even if you just write that, right? I mean, I'm going to assume that you actually did it so that you would find solutions that don't work, but you don't necessarily need to write down the checking part. You do that in a calculator. You can do it by kind of inspection, like looking and knowing, I'm just making sure that none of the denominators turn out to be 0, right? But do something, right? So again, that I can tell what you're thinking about as you go through it. Does that make sense? Okay. Now it might only cost you 2 points or something, but again, those add up if it's happening all over the place. So, okay. Everybody good? Okay. One last thing real quick. We'll pick up with this stuff tomorrow. Like we don't have any extra stuff to talk about. We'll look at how this works for inequalities, but it's not really anything new. C should be very similar. So, do that one. D looks different though, right? Everything else we've been doing, we've been looking at, rational expressions, fractions that have X in the denominator. And then this thing rolls up with its negative powers and kind of looks like a whole different thing, right? What do negative exponents mean? It's not a square root, but I mean, for it to fit, unless I've just put this in the wrong place, right? It's got to somehow mean that it turns the thing into a fraction, right? So what a negative exponent does is kick the thing with the exponent down into the denominator, right? It's a reciprocal. Negative exponents are reciprocals. So like a -1 power just means the reciprocal of whatever the power is. So like 5 to the minus 1 is 1/5. So x to the negative 4 is the same thing as 1 over x to the 4th, or the reciprocal of x to the 4th. Minus 4 is, of course, just minus 4. This middle term is the one that tends to throw people off, right? I know, maybe we need a reminder about how negative exponents work, but this is the place where people usually get tripped up. What's the exponent on there? Is it on the whole thing or just part of it? It's x to the negative 2 and 3 copies of them, right? It's 3 times a thing raised to a power. Order of operation stuff, exponents happen before multiplication does, right? So x to the minus 2, which is the reciprocal of x squared, and 3 copies of it. Or more commonly, we would probably write that like this. But the point is that the 3 doesn't move into the denominator with it, right? That's what would happen if you had, those grouped. Then the 3 would go along with, right? And it would be the whole thing squared. Since this is 3 times x to the minus 2 for like order of operations purposes, the x squared is the only thing that moves down. And then this, once we've rewritten it, this should be a lot more, in the wheelhouse of stuff we've been talking about. There are a few ways you can go about doing this, but I want you to try first. So try to finish that one. Do C, give D a shot, do some homework, and I'll see you guys tomorrow.